The interstellar comet 3I/Atlas has emerged as an object of immense scientific fascination and public attention since its discovery, but the recent and definitive confirmation of its rare anti-tail has raised its profile to a new level of intrigue. What was initially a suspicion presented in a study in August has now become an astronomical fact validated by new and complementary observations, detailed in a technical paper available as a preprint on the AR-14 server, cementing the idea that 3I/Atlas exhibits an exceptional phenomenon. This inverted tail or anti-tail is not merely a visual curiosity, but an element that offers crucial insights into the internal mechanics and composition of visitors traveling through deep space, challenging pre-existing models and stimulating a new focus of research on the physical processes of transsolar objects that cross our solar system. The importance of 3I/Atlas is heightened by its historical context. Discovered in July through the Asteroid Terrestrial Impact Last Alert System ATLAS, a NASA-funded project, this unique object became only the third confirmed interstellar visitor observed transiting the solar system's borders, and notably, the fastest detected to date. Its arrival followed the iconic asteroid 1I/Oumuamua, sighted in 2017, and the comet 2I/Borisov, documented in 2019, placing it in an extremely restricted and precious lineage of cosmic objects that carry direct clues about distant stellar environments. Confirmation of the anti-tail, specifically, was achieved through a meticulous observational effort, mobilizing the technical capabilities of cutting-edge telescopes located at the W.M. Keck Observatory in Hawaii, whose high sensitivity and strategic location atop Mauna Kea ensured the acquisition of the data necessary to validate the initial observations. The appearance of an anti-tail, while a remarkably rare occurrence in comet observation, is not entirely unknown in astrophysics, though its appearance is always a subject of intense scrutiny. This unusual feature is one of the elements that still deeply intrigues scientists and inevitably incites public speculation that often leans into the realm of science fiction, including conspiracy theories about alien technology or life. However, science establishes a clear precedent that such tales have been recorded on other historical comets. What underlies the phenomenon, in most cases, relates to the fundamental physics of comets. When they approach the sun's heat and radiation, they experience the sublimation of their frozen volatile materials. This essential process expels gases and dust particles that form the coma, the nebulous sphere or coma that surrounds and defines the object's nucleus. Under typical conditions, a comet's tail is created in a linear and predictable fashion, as both solar radiation pressure and the solar wind, a constant stream of charged particles emanating from the sun, blow the dust and gas ejected from the coma systematically and precisely away from the central star. The spectacle of an anti-tail breaks this visual norm, giving the opposite appearance, where the tail projects toward the sun or in the direction of the comet's motion. The overwhelming majority of these sightings, as clarified by entities such as the European Space Agency, ESA, are classified as an ingenious but disarming optical illusion. In these scenarios, the actual physical tail still points rigidly away from the sun, driven by the stellar wind. However, it is the specific angular perspective of the Earth's observation point relative to the comet's orbital path and the plane of the solar system that distorts visual perception, causing a portion of the tail, composed of larger particles, to appear to extend in the opposite direction, that is, in front of or behind the comet's nucleus in an inverted fashion. The complexity and fascination surrounding 3I/Atlas lies in the fact that the new observations suggest that its particular anti-tail may not be merely a perspective-based optical illusion, distinguishing it from the classic archetype of the phenomenon. This intriguing distinction was supported by observations conducted when the comet was at a considerable distance of 3.8 astronomical units, AU, from the Sun, equivalent to approximately 570 million kilometers. At this distance, astronomers detected an elongation of the coma that actually pointed in the solar direction. If this tail were composed of light particles driven by the solar wind, its direction would be expected to be away from the sun. Its apparent sunward orientation suggests the influence of gravitational or inertial forces on ejected material that go beyond the full domain of wind and radiation pressure. Seeking a more robust physical explanation for this anomalous nature, astronomy professor Jason Wright of Pennsylvania State University confirmed in a statement to IFL Science that the observation of this type of antitail is not entirely unprecedented, pointing to the documented case of comet Kohoutek, observed in 1974. As a parallel, the basis of the specific phenomenon is the mechanics of larger ejecta. When particles of greater mass are released from the comet's nucleus, their inertia is such that they are less susceptible to the thrust of the solar wind and radiation pressure compared to the finer gas and dust. Instead of being blown radially away from the sun, these larger particles remain substantially bound to the comet's pre-existing gravitational orbit. This alignment causes material to follow, either ahead of or behind the nucleus, forming streams that, depending on the viewing angle, project into an apparent long plume of material that appears to be inverted or ahead. The difference in particle behavior is vital to understanding 3I/Atlas, as explained by Dr. Michael Bush, a postdoctoral fellow in astronomy and astrophysics at the U.S. National Science Foundation, NSF. According to his explanation, the finer particles of gas and dust are consistently and efficiently pushed away from the sun by the solar wind, forming the classic tail. By contrast, the heavier fragments and chunks, resisting the rapid push of radiation, end up spread more widely along the entire curve of the comet's orbit. It is this vast scattering of denser material along and near the comet's orbit that gives the illusory appearance of a tail pointing forward or in the apparent direction of orbital motion. Furthermore, this dynamic of larger fragments following the orbit not only generates the antitail, but also has the potential to seed meteoroid streams along the comet's entire trajectory, promising future meteor displays as the solar system crosses the trail left by 3I/Atlas. Recent research has gone beyond tail morphology, delving into the analysis of the chemical composition of 3I/Atlas's coma, a field that has revealed additional, if not even more enigmatic, insights into the nature of this interstellar object. Scientists reported a peculiar chemical distribution. Nickel Ni was concentrated in an unusually dense manner near the cometary nucleus, suggesting a robust and highly localized source of metallic material. In contrast, cyanide CN, a molecular compound common in comets, exhibited a more mysterious and widespread dispersion within the coma, contradicting the distribution expected under certain sublimation models. This dichotomy in chemical distribution, concentrated nickel versus dispersed cyanide, constitute a unique internal signature for 3I/Atlas, indicating physical processes or reactions occur within or just outside the nucleus that are not yet fully understood by current cometary science. This reinforces the idea that interstellar objects may possess fundamentally distinct architectures and chemical dynamics from comets originating from our own Oort cloud. Ultimately, the validated antitail phenomenon, especially because it suggests an etiology beyond mere perspective illusion, constitutes an additional and essential piece in the already vast and complex puzzle that the interstellar visitor 3I/Atlas represents for the scientific community. Analyzing in depth not only this rare morphological behavior, but also its peculiar and unexpected chemical signature, such as concentrated nickel and dispersed cyanide, promises to allow scientists to better understand the structural diversity, material variety, and dynamics of objects that originate outside our star system and occasionally invade it. Scientists continue their work observing 3I/Atlas with continuous surveillance as it moves away from our side of the sun and reappears from Earth's opposite perspective, knowing that each new piece of data collected contributes incrementally but significantly to a clearer picture of the physics and surprises that lie hidden in the universe.